Hey there and welcome. Today we're going to tackle a classic physics problem, one that really messes with your intuition. It's all about what happens when you're on something that's spinning and how the normal rules of motion kind of get thrown out the window. We're going to be exploring some really cool invisible forces.
You've been on a merry-go-round, right? And you try to walk in a straight line from the center to the edge? You feel that weird invisible push to the side, trying to throw you off balance? Well, that mysterious little shove, that is a perfect real-world taste of the Coriolis force, which is exactly what we're diving into today. All right, let's jump in. Here's our game plan. First, we'll break down the problem itself. Then, we'll get into why a spinning world is so tricky, which, you guessed it, leads us straight to the Coriolis force. The real key, though, is going to be finding the object's true velocity. Once we have that, we can finally calculate the force and, most importantly, review the common mistakes so you don't make them. Okay, let's set the stage. I want you to picture a smooth, horizontal rod spinning around one of its ends, kind of like a helicopter blade or a single hand on a clock, just spinning flat. Now, imagine a little bead or a sleeve that can slide freely along that spinning rod. That's our setup. So here are the nitty-gritty details. We've got this rod spinning at a constant rate, which we call omega. A sleeve starts right at the center, the axis, and gets a little push, so it starts sliding outwards with an initial speed of v0. Our mission, should we choose to accept it, is to figure out the exact strength of that sideways Coriolis force at the very moment the sleeve is 50 centimeters out from the center. All right, first things first. Before you solve any physics problem, you got to get organized. This is all the information they gave us, our knowns. We've got the angular velocity, omega, the sleeve's mass, m, its starting speed, v0, and the final spot we care about, r. Seriously, laying it all out like this first will make the rest of our lives so much easier. Okay, so now we get to the core of what makes this problem so interesting. It's a real brain teaser. See, we're not watching this happen from the nice, stable ground. Our point of view, our reference frame, is actually on the spinning rod. And that little detail, that rotation, completely changes the rules of the game. And this brings us to a super important idea, the non-inertial reference frame. Now, that just sounds fancy. All it means is that our viewpoint is moving, it's accelerating, or, like in our case, it's rotating. In frames like these, Newton's good old laws of motion don't quite work as expected. To make them work, we have to invent a couple of what we call fictitious forces, just to explain the weird things we see happening because of our own motion. To really get this, let's put them side by side. An inertial frame, that's like standing still on the ground. No acceleration. An object goes in a straight line unless a real force pushes it. But in our non-inertial frame, stuck on the spinning rod, these fictitious forces pop up out of nowhere, and paths that should be straight suddenly look curved. It's all about perspective. So, from our spot on that spinning rod, we'd feel two of these apparent forces acting on our little sleeve. First, there's the centrifugal force. That's the one that feels like it's flinging the sleeve outward, away from the center. And then, second, you have the star of our show today, the Coriolis force. Okay, let's put our star player under the microscope. It's time to officially meet the Coriolis force and figure out how we can actually describe it using math. This formula right here is the whole key. The Coriolis force, Fc, is equal to 2 times the mass times this thing called the cross product of the sleeve's velocity, v', and the rod's angular velocity, omega. Now, don't let the cross product scare you. For our problem, all you need to know is that it means the direction of the force is always sideways. It's perpendicular to both the direction the sleeve is sliding and the axis the rod is spinning around. That's where the sideways push comes from. So let's break that formula down. We know m, that's the mass. We know omega, that's how fast the rod is spinning. But the most important, and by far the trickiest variable here, is v'. This is not just any velocity. It is specifically the sleeve's velocity as you would measure it from the spinning rod. Getting this one right is the absolute secret to solving this problem. And that brings us to the number one pitfall. This is the mistake almost everyone makes the first time. It is so tempting to just look at our list of knowns, see that initial velocity v0, and just plug it into the formula for v'. But is that right? Think about it. Is the sleeve really still moving at 1 meters per second by the time it gets to the 50 centimeter mark? The answer to that question is a definite 100% no. The sleeve's velocity has changed, so we have to figure out its new speed, its instantaneous velocity, at that exact point. But What force could possibly be acting on it to speed it up as it moves outward? The answer is that other fictitious force we talked about, the centrifugal force. From the rod's perspective, this force is constantly pushing the sleeve outwards, away from the center. And a constant push means a constant acceleration, right? This force is doing work on the sleeve, basically pumping energy into it, and that makes it speed up as it slides out. So how in the world do we calculate this new speed? Well, we start with our old friend F equals ma, but we use it from the rod's point of view. The only force pushing it outward is the centrifugal force, which has a formula, m omega squared r. So we set ma equal to m omega squared r. The masses cancel out, which is nice. Now, because the acceleration depends on the distance r, it's not constant, so we have to use a little bit of calculus. We integrate. And when all the dust settles, we get this really neat final expression for v prime. You can see it includes both the initial speed and the speed it gained from that centrifugal push. Fantastic! We've done the heavy lifting. We've figured out the conceptual puzzle and found the correct velocity. Now we have all the pieces we need to just put them together and calculate our final answer. Here's our final data sheet. We've got all the stuff they gave us, and now we can add our brand new hard-earned value for v prime. If you plug in the numbers, the speed at 50 centimeters is about 1.414 meters per second. And just look at that. That's a lot faster than the 1 meter per second it started with. The centripetal force really did its job. Now for the grand finale. We take our Coriolis formula and we plug in our calculated velocity, not the initial one. And remember that tricky cross product? Well, since the sleeve is moving straight out and the rod is spinning, everything's at a perfect right angle. That makes the math super simple. We can just multiply everything together. So we plug in our numbers, 2 times the mass, times our new velocity, times the angular velocity, which gives us our answer. The magnitude of the Coriolis force at that exact moment is 2.8 newtons. We did it. We found the strength of that mysterious sideways push. Now look, we didn't just find an answer to a single problem. We learned the process. So let's just take a second to recap the most important lessons here, so they really stick with you. These are the 3 things you have to check every single time you see a problem with a rotating system. First, ask yourself, am I spinning? Identify that reference frame. Second, account for all the apparent forces. In our case, the centripetal force was the hidden culprit that changed everything. And finally, and this is the big one, always use the instantaneous velocity, v prime, in that Coriolis formula. If you can remember these 3 things, you'll nail these problems every time. You know, we just cracked a textbook problem about a tiny little sleeve on a spinning rod, but this is so much bigger than that. Now that you've seen how to handle it for a simple system, I want you to think about this. Where else does this exact same force, born from nothing more than motion in a rotating frame, totally shape our world? We're talking about the swirl of hurricanes, the currents in the ocean, even the path of long-range missiles. The Coriolis effect is literally everywhere. What are you going to see differently now?